All right, so we'll try this lecture this way. Try to save us some time in class. So if you can watch this, this will kind of introduce you to electrical circuits, kind of ties with the first couple of modules, even parts of module 3. So um, this PowerPoint, I'm going to pull this PowerPoint up so y'all can see it. All right, so this PowerPoint is located in Blackboard. Um, so you'll have access to this as well. You're welcome to pull that back up. But at this time, we're just going to kind of run through it as quick as we can. So electrical fundamentals, electrical principles, how electricity works in general, kind of from a scientific standpoint, and then applying that to real life. So this isn't the book PowerPoint. That one's also available as well. And I may reference that one at times, but for now I'm going to go through this one. It seems like it has more visuals. Seems to be a little more user friendly. So thought I'd use this one. So you can reference the book one as well. So I'm not going to spend a lot of time getting into the chemical structure of things because, to be honest with you, I failed chemistry when I was in college, so it's not my strong suit. So you can look through that, how things are charged, protons, neutrons, electrons. So we're working with all these things in electricity. The electrons is what we're moving through the circuit, and so I'm just kind of skipping through all this. Not going to get into a lot. Conductors, anything that's a good conductor, metals, aluminum, copper, gold, silver, those things are really good conductors, and it all has to do with their chemical makeup. So you can dig more into that if you're so inclined, but that's why we use those things for our wire. That's why those things are good conductors, and they're also, if they're a good conductor for electricity, they're a good conductor for heat. So anytime we're talking about heat loads, for example, certain materials have a value that will conduct heat better than others. So things that are good insulators help stop the flow of heat or stop the flow of electricity. So there's copper. Going to skip on through this. All right, so kind of introducing you to Ohm's law. And this may not be exactly where we start in lab, but it will be probably our second lab. So we probably won't get to it during the first lab, but we will get to it through the second. So it's something you're going to need to know pretty soon. 1 volt will push 1 amp through 1 ohm of resistance. Now, what does that mean? Well, what that means is voltage is essentially a force. So you have a certain amount of voltage, whether it be 120 volts, 24 volts, 240 volts, 208, and 480. That's kind of the ones that we commonly work with, especially in lab, and that you're going to work with in this field. So you're not going to have, you're not going to be working with super high voltage unless you're an electrician. 480 is about as high as any of our stuff goes that I know of. So at least in the lab for sure. So what does that mean that it's the force? Well, the electrons are already present in the wire. In the copper wire, there are electrons present. Those electrons have to be moving in order for that current to flow. So when you apply voltage to the circuit, those electrons start to move, and as they move, then they can move that power through the circuit to the things that need the power. So to switches, to loads, what's the difference between a switch and a load? Power passing things that pass power. Switches, things that consume power. Those are your loads. So examples of loads would be light bulbs, motors, anything that we're trying to control to do some sort of work. And the controls themselves are switches. They're the things that's telling it when to come on and when to come off. So they're the ones that's breaking the flow of electrons. So you've got that electromotive force, or EMF, and then you've got intensity, which is your amperage. and then you've got resistance. So this is your basic Ohm's law formula, which is E equals I times R. Um, so we'll get into a little bit more about what each of those mean, but voltage is your force, amperage is your intensity or current. That's the flow. It's got to be moving, and that's how intense that it is moving. And then resistance is resistance to flow. So every circuit has to have some sort of resistance, whether it's in a form of a motor or a light bulb or whatever it may be. Something that's going to consume power. So these are the three that we're working with, and then you're also going to bring power in, which is watts, real soon. So you've got E, I, R, and P, which is power. So your basic formula is E equals I times R, or volts equals amps times resistance. So kind of the formula, and then the realistic thing, like when we're measuring volts, or we can measure amps and we can measure resistance. I don't know why they don't just use that, but they don't. So E equals I times R is our formula. So if we're wanting to solve for one of the unknowns, so for example, if I know voltage and I know resistance, I'm trying to find amperage. If I know any of the two, I can find the other two. So the second one, the other one being power. If I know any two, I can find the other two by using these formulas. So why does that help me? Because it helps me know, one, if my meter is doing what it's supposed to be doing, if it's accurate. It also lets me know what to expect. For example, like if I was hooking up a bunch of light bulbs in a house and I needed to know what size circuit to run them on, I would need to know how many amps that all those were drawing, so I would know how to size that system. So I could calculate that by using Ohm's law. All right, so I'm not going to spend a ton of time on this because it kind of gets redundant, but this goes through the algebra of it all, the math behind it. So here's your example. So all these numbers should add up if you're calculating it. So if you know that, for example, you have a circuit that's drawing 2 amps and its resistance is 5 ohms, then the voltage drop across that should be 10 volts. Or if you're applying 10 volts to the circuit and you know that the circuit has a resistance of 5 ohms, then you can calculate expected amperage just by using these formulas. So you can move those numbers around from side to side. Like I said, I'm moving pretty quick through this because we'll probably go through it in class, but I just want to touch base on it a little bit, give you a couple of examples. All right, so here's the first example. So I'll give you a second to look at this. All right, so what is voltage supplied to the following circuit? What is the voltage supplied? So because all these are related, if I know these two values, I can find the other values. So I know that the resistance of this particular resistor or heater or whatever it may be has a resistance of 24 ohms. I know that it's drawing 5 amps of current, which means that's the intensity of the flow. So what is the voltage given those numbers? So you're just going to plug those in for your E equals I times R. So your E is your unknown, E is your voltage, electromotive force, and amps is your intensity, and 24 ohms is your resistance. So plug those in. 5 times 24 equals 120. So that would be your applied voltage there. Next example. Assuming that I know voltage, what would happen if I change resistance? So in this case, maybe it's still the 120 volt circuit and I've got a different resistor, 10 ohms instead of what the last one was. What would be your amperage now? How would you do that? Well, E equals I times R, you could plug those in. You could do 120 equals I times 10, or you could go ahead and move those over now. So what they did is they went ahead and moved the I over and got it by itself, solved for I, by crossing over and bringing over the E and the R. So to undo multiplication, you have to divide. So in order to get rid of this R with the I, you got to divide by R. do the same thing on the other side. So E divided by R equals I. Now, so what does that look like? Well, I plug in 120, plug in my 10, I divide those out. What's my expected amperage? 12 amps. All right, so that's it in a nutshell. I'm not going to go through a bunch more of those, but that's kind of how that should work. All right, so here's one of the easier ways to learn this. If you can imagine this circle, this is your wheel or your disc. So this is your same formula, but it's just kind of put in more of a visual form. So you've got your E, which is your voltage, your I, which is your amperage, and your R, which is your resistance or your ohms. And it's E on the top, I times R. So if you're looking at where my cursor is, if you can see that, you've got the E on the top, and then this line here, just imagine that's your equals. And then I and R are beside each other, equals I times R. Now, if you're wanting to solve for one of the others, so let's say, for example, you didn't want to do all that algebra, move those things over, and you wanted to know the formula. So I said use this as equals, but I meant to say, imagine this line is divide. So this line under the E is a dividing line. I, and this line going down is multiplication. So what is your formula for E equals I times R, right? Now what if I want to solve for current? Which letter, first of all? I, intensity. So you cover up the one that you're trying to solve for, and that gives you the formula for it. So just cover it up with your thumb, or imagine that you are covering it up with your thumb. I equals E divided by R. So then you could just plug in the one, find the one you don't know by plugging in the two that you do. Same thing there. R equals E divided by I. So there's just kind of a breakdown on it. There's your formulas. Calculating power. So power is the rate at which we're doing work. So we're applying voltage through resistance to do work and to do some sort of electrical work. Power is the rate at which we do the work. Amperage is the intensity at which the work is done, how hard it's working. So the formula for power is, the basic formula is P equals I times E, which is pi, I'll remember it that way, which is power equals amps times volts. What's the power consumption of an electric circuit using 15 amps, 120 volts? You plug that into your formula, and your wattage would be 1800 in that example. Skipping through all these. Okay. Let's see here. All right, so we had our basic wheel, which was the little E, and E was I times R. And there's also one for P equals, I over E, whatever. But this one is more expanded. This gives you all of your formulas kind of in one. So I like both of these for different reasons. I like the first one because it's really simple, and I like this one because it shows me everything. So you'll want to keep both of these on hand, at least till you get used to it. So how do we use this? It looks like something pretty involved. But really, essentially, you can break this thing down in fourths. So if you go back, you look at your basic four components, power. What are the formulas for power? Well, here's the different formulas. So if you were to do that math and you were to calculate all those out, you could find some of those formulas. Now, some of those you might not be able to find as easy, so you can use these. Use your expanded formulas. That's what I would call these. So, for example, if I'm trying to take the one that I'm trying to find, which in this case, for example, if I'm trying to find power, and I know two of the other values, I can find any of the other two. So if I'm trying to find power and I know current and I know resistance, then I can use that middle formula. E equals I squared times R. If I know voltage and I know resistance, then I'd use E squared over R. And if I knew voltage and intensity or current, amperage, then I'd use this formula. So it's just, all it's saying is what's the one you want to find and what's the two that you already know. And so I'll have this as a handout that you can print off. All right, so what is resistance in the first place? Well, resistance is measured in ohms. So we learn how to do that with our meter to check ohms across something. We know that when we set it to ohms or resistance, not only are we measuring resistance, but we're also measuring continuity. So it's showing that those 2 points are continuous, that they're touching each other, or that they're open, right? So you've got different readings on your meter. You could have an OL. OL means open loop, which means that they are not connected. Zero ohms means that they are connected, but there's no resistance. But there is still continuity. And then when you actually read a reading, let's say you read 6.75 or whatever, that would be continuity and resistance. So 3 different things that your ohm meter is telling you. But in order for a circuit to work without being a short circuit, you have to have a load if there's some sort of resistance in the circuit. Because if not, it just creates a short, and then that creates all kinds of problems. All right, so here's where your terminologies get a little bit weird, and I mentioned these earlier. Mentioned OL and zero and all that. So let's kind of summarize this. Sometimes this is confusing. Sometimes it helps people make sense. So yeah, I'll throw it out there and you can take it as you want. So resistance is the open space between the shores of this picture. So here's the picture they're referring to. So here's your little stadium over here on the left. You got a big parking lot. You've got a river that you're trying to get across to. You're trying to get, these cars are trying to get across so they can park in this parking lot. How are they going to get there? Well, right now, there's no way to get there. So there is infinite resistance, which means everywhere they go, there's resistance. They can't get across. So what does infinite resistance mean? This is your OL. This is your open loop. So there's no continuity between the left side and the right side. So it is infinitely open. So this would be like taking your meter leads, sticking them up in the air, putting it on ohms, and it's reading nothing because there's infinite resistance. Like there's no way they're ever going to touch each other. All right, so what if we add a load? What if we add some sort of path? We add a light bulb, for example. So the load provides a path for the electrons, place for it to go, place for it to become consumed, or work to be done. There's resistance to flow, but it's no longer infinite resistance. So now it has a number, it has a value. So let's say we put in a little bridge down here. Small load provides a path for some of the electrons, and now you can start seeing that things are coming across, but is there an easy path for everybody, or is there still high resistance? Still high resistance. So what if I lower the resistance? What would that look like? Adding more bridges, more load. All right, resistance is lower, which means more electrons, more current flows. However, so resistance is good. We got to have some sort of resistance in the circuit, keep it from being a short. But what if we have no resistance? So that would be your zero, right? So infinite resistance is your OL. Some resistance is a number, and then no resistance or low resistance is 0.0 or right around 0. What does that mean? Why is that bad? Well, it's not always bad, depending on what I'm checking. If I'm checking a switch to see if it's open or closed, 0 is fine. That's what I'm expecting it to say. But if I'm checking a load or across the entire circuit, I need to have resistance somewhere. And if I don't, if I have no resistance to it, then what's going to happen? So now these cars all come in at 100 miles an hour, and instead of having to slow down before they enter the parking lot, they just drive in 100 miles an hour and they all crash, right? That's kind of what electricity is doing if it bypasses the load, if it bypasses the resistance. There's no way for it to be um, contained, I guess, or consumed. So that's bad. So zero resistance in a circuit is bad. All right, so how are these all related besides just being in a formula together? Resistance affects amps and watts. Also affects the voltage drop across something, so they're all tied together. The lower a load's resistance, the higher its amps and watts. So here's another visual representation of what we just talked about. So the top one will be open, infinite resistance. That's your OL. This one has some resistance. And you could do your Ohm's law and calculate those out. Those should add up. So notice how your wattage changes and your amperage changes. And then the last one will be no ohms, no resistance, 0.0 on your meter. And that's where you're going to start tripping breakers and stuff. All right, so that's an introduction to Ohm's law. It's nothing in depth, but at least it gives you an idea where we're going. So I'll be adding some more stuff later.